In this section, we will take a look behind the scenes of JavaScript and learn how the language actually works. So, throughout this section, we will take your basic knowledge of JavaScript and elevate it to a completely new level, where you will then understand exactly how everything that you learned before actually works under the hood. And this is actually extremely important, because this knowledge will really empower you to write better code and to understand other developers' code. And so, in the end, it will make you a better, more confident, and more successful developer. Now, I'm telling you all this because some people find this kind of theory lectures boring for some reason. But they are really not. And I actually invested well over a month into building this section alone. And so that might show you just how crucial this information is. And finally, knowing how JavaScript really works will also set you apart from the competition, because many other junior developers simply don't know about much of this stuff. So don't be scared of theory, and let's get started. As an introduction to this theory section, I want to start with a very cool and very high-level overview about the JavaScript language, just so you get a first overview of most of the things that we need to learn in order to eventually master JavaScript. And this is going to be a long lecture, so get ready for a crazy ride. And I want to start by coming back to that first definition that I gave you on JavaScript, where I told you that JavaScript is a high-level, object-oriented, multi-paradigm programming language. Now, this is of course 100% correct, but it's also really just the surface, the tip of the iceberg. So what about this definition? JavaScript is a high-level, prototype-based, object-oriented, multi-paradigm, interpreted, or just-in-time compiled, dynamic, single-threaded, garbage-collected programming language with first-class functions and a non-blocking event loop concurrency model. Wait, what? Is this some kind of joke? Well, yeah, it kind of is, actually. I just packed as much information as possible about JavaScript into one unreadable sentence just for fun. But besides fun, this also gives us a great opportunity to unpack all of this in order to get a first peek into all the stuff that we're going to learn about JavaScript throughout the course. And this is not to intimidate you. It's really not. I just want you to get the big picture before really getting started, and also introduce some topics that are just good to know. Because getting the big picture before diving deep is, in my opinion, an amazing learning technique. So with that being said, let's unpack this now a little bit. So these are the 9 JavaScript topics that we're briefly going to talk about in this lecture, slightly reordered. And starting with the high-level part, as you might already know, every program that runs on your computer needs some hardware resources, such as memory and a CPU, to do its work. Now, there are low-level languages, such as C, where you have to manually manage these resources. For example, asking the computer for memory to create a new variable. On the other side, you have high-level languages, such as JavaScript and Python, where we do not have to manage resources at all, because these languages have so-called abstractions that take all of that work away from us. This makes the language easier to learn and to use, but the downside is that programs will never be as fast or as optimized as, for example, C programs. Now, one of the powerful tools that takes memory management away from us developers is garbage collection, which is basically an algorithm inside the JavaScript engine which automatically removes old unused objects from the computer memory in order not to clog it up with unnecessary stuff. So it's a little bit like JavaScript has a cleaning guy who cleans our memory from time to time so that we don't have to do it manually in our code. Next up, JavaScript is an interpreted or just-in-time compiled language. And again, we will learn more about this in this section, but what you need to know for now is that the computer's processor only understands zeros and ones. That's right. Ultimately, every single program needs to be written in zeros and ones, which is also called machine code. And since that's not really practical to write, is it? We simply write human-readable JavaScript code, which is an abstraction over machine code. But this code eventually needs to be translated to machine code, and that step can be either compiling or interpreting. This step is necessary in every single programming language because no one writes machine code manually. In the case of JavaScript, this happens inside the JavaScript engine. Now, one of the things that makes JavaScript so popular is the fact that it's a multi-paradigm language. In programming, a paradigm is an approach and an overall mindset of structuring our code, which will ultimately direct the coding style and technique in a project that uses a certain paradigm. And this definition still sounds kind of abstract, but don't worry, it will become more clear as we move on. Now, three popular paradigms are procedural, object-oriented, and functional programming. So procedural programming is what we've been doing so far, which is basically just organizing the code in a very linear way, and then with some functions in between. Now about object-oriented programming and functional programming, I will talk about them in a second. Also, we can classify paradigms as imperative or as declarative. But again, more on that later. Now, many languages are only procedural or only object-oriented or only functional. But JavaScript does all of it. So it's really flexible and versatile, and so we can do really whatever we want with it. It's our choice. We can use whatever paradigm we want. And in this course, I will show you how to use all of them. So, about the object-oriented nature of JavaScript, it is a prototype-based object-oriented approach. Now, what does that mean? Well, first, almost everything in JavaScript is an object, except for primitive values such as numbers, strings, etc. But arrays, for example, are just object, and we already saw that in practice, right? Now, have you ever wondered why we can create an array and then use the push method on it, for example? Well, it's because of prototypal inheritance. Basically, we create arrays from an array blueprint, which is like a template, and this is called the prototype. This prototype contains all the array methods, and the arrays that we create in our code then inherit the methods from the blueprint, so that we can use them on the arrays. And this, what I just explained to you, is actually a huge oversimplification, which might still sound confusing, and that's the reason why there is a whole section on object-oriented programming with JavaScript later in the course. But since this is a big overview lecture, I wanted to first introduce this topic right here. Next up, JavaScript is a language with first-class functions, which simply means that functions are treated just as regular variables. So we can pass functions into other functions, and we can even return functions from functions. And this is extremely powerful because it allows us to use a lot of powerful techniques and also allows for functional programming, which is one of the paradigms that we just talked about before. And in fact, we have already used the power of first-class functions without knowing that they are called first-class functions. So remember this piece of code that we wrote for closing the modal window that we built before. So right here, we pass the close modal function into the add event listener function, as if it was just a regular variable, right? And actually, not all languages have first-class functions, but JavaScript has, and it is amazing. Believe me, it's really, really helpful. Next, I said that JavaScript is a dynamic language, and dynamic actually means dynamically typed. So as we've already seen, in JavaScript, we don't assign data types to variables. Instead, they only became known when the JavaScript engine executes our code. Also, the type of variables can easily be changed as we reassign variables. And this is basically what dynamically typed means. Now, there is a lot of controversy if this is good or bad, but this is just how it works. Now, the same is not true for most other programming languages, where we have to manually assign types to variables. And this then usually prevents bugs from happening, which is the reason why many people say that JavaScript should be a strongly typed language as well. And if you yourself want to use JavaScript with types, then you can always look into TypeScript. But anyway, let's now finally talk about the single thread and the non-blocking event loop concurrency model. Now, this is a really complex topic, and probably the most complex one of the whole course, which is why it's kind of at the end of the course. And therefore, I'm not going to go into specifics here just yet, but instead I will just define some things here. First, what actually is a concurrency model? Well, it's just a fancy term that means how the JavaScript engine handles multiple tasks happening at the same time. Now, okay, that's cool, but why do we need that? Well, because JavaScript itself runs in one single thread, which means that it can only do one thing at a time. And therefore, we need a way of handling multiple things happening at the same time. And by the way, in computing, a thread is like a set of instructions that is executed in the computer's CPU. So basically, the thread is where our code is actually executed in the machine's processor. All right, but what if there is a long-running task, like fetching data from a remote server? Well, it sounds like that would block the single thread where the code is running, right? But of course, we don't want that. What we want is so-called non-blocking behavior. And how do we achieve that? Well, by using a so-called event loop. The event loop takes long-running tasks, executes them in the background, and then puts them back in the main thread once they are finished. And this is, in a nutshell, JavaScript's non-blocking event loop concurrency model with a single thread. It sounds like a mouthful for sure, but in the end, it really just compresses to this. Just keep in mind that, again, this is a huge oversimplification that we will come back to. All right, and this actually rounds up this overview lecture. I know there was a ton of stuff to take in, but I hope that you still learned a thing or two here. So I talked about the JavaScript engine in the last lecture, but what is that engine actually? And what is a JavaScript runtime? Also, how is JavaScript code translated to machine code? So that's just some of the topics that we talked about in the last video, and so now let's find out how they work in this lecture. So a JavaScript engine is simply a computer program that executes JavaScript code. There are a lot of steps involved in doing that, but essentially executing JavaScript code is what an engine does. Now, every browser has its own JavaScript engine, but probably the most well-known engine is Google's V8. The V8 engine powers Google Chrome, but also Node.js, which is that JavaScript runtime that we talked about in the beginning of the course. So the one that we can use to build server-side applications with JavaScript, so outside of any browser. And of course, all the other browsers have their own JavaScript engines, which you can look up online if you're interested. Anyway, it's quite easy to understand what an engine is. But what's most important is to actually understand its components and how it works. So any JavaScript engine always contains a call stack and a heap. The call stack is where our code is actually executed using something called execution contexts. Then the heap is an unstructured memory pool which stores all the objects that our application needs. All right, so with this look at the engine, we have answered where our code is executed. But now the question is how the code is compiled to machine code so that it actually can be executed afterwards. Well, let's find out. But first, we need to make a quick computer science side note here and talk about the difference between compilation and interpretation. So in the last lecture, we learned that the computer's processor only understands zeros and ones, and that therefore every single computer program ultimately needs to be converted into this machine code. And this can happen using compilation or interpretation. So in compilation, the entire source code is converted into machine code at once. And this machine code is then written into a portable file that can be executed on any computer. So we have two different steps here. First, the machine code is built, and then it is executed in the CPU, so in the processor. And the execution can happen way after the compilation, of course. For example, any application that you're using on your computer right now has been compiled before, and you are now executing it way after its compilation. Now, on the other hand, in interpretation, there is an interpreter which runs through the source code and executes it line by line. So here we do not have the same two steps as before. Instead, the code is read and executed all at the same time. Of course, the source code still needs to be converted into machine code, but it simply happens right before it's executed and not ahead of time. Now, JavaScript used to be a purely interpreted language, but the problem with interpreted languages is that they are much, much slower than compiled languages. This used to be okay for JavaScript, but now with modern JavaScript and fully fledged web applications that we build and use today, low performance is no longer acceptable. Just imagine you were using Google Maps in your browser and you were dragging the map, and each time you dragged, it would take 1 second for it to move. That would be completely unacceptable, right? Now, many people still think that JavaScript is an interpreted language, but that's not really true anymore. So instead of simple interpretation, modern JavaScript engine now use a mix between compilation and interpretation, which is called just-in-time compilation. This approach basically compiles the entire code into machine code at once and then executes it right away. So we still have the two steps of regular ahead-of-time compilation, but there is no portable file to execute, and the execution happens immediately after compilation. And this is perfect for JavaScript, as it's really a lot faster than just executing code line by line. Now, I skimmed over some details here, but this is really all you need to know. Anyway, let's now understand how this works in the particular case of JavaScript. So, as a piece of JavaScript code enters the engine, the first step is to parse the code, which essentially means to read the code. During the parsing process, the code is parsed into a data structure called the Abstract Syntax Tree, or AST. This works by first splitting up each line of code into pieces that are meaningful to the language, like the const or function keywords, and then saving all these pieces into the tree in a structured way. This step also checks if there are any syntax errors, and the resulting tree will later be used to generate the machine code. Now let's say we have a very simple program. All it does is to declare a variable like this. And this is what the AST for just this one line of code looks like. So we have a variable declaration, which should be a constant with the name x and the value of 23. And besides that, there is a lot of other stuff here, as you can see. So just imagine what it would look like for a large, real application. And of course, you don't need to know what an AST looks like. This is just for curiosity, okay? Now, sometimes I get asked if this tree has anything to do with the DOM tree. And the answer is a very clear no. So this tree has absolutely nothing to do with the DOM. It is not related in any way. It's just a representation of our entire code inside the engine. Anyway, the next step is compilation, which takes the generated AST and compiles it into machine code, just as we learned in the previous slide. This machine code then gets executed right away, because remember, modern JavaScript engine use just-in-time compilation. And remember, execution happens in the JavaScript engine's call stack. But we will dig deeper into this in the next lecture. Alright, so far so good. We have our code running, so we can finish here, right? Well, not so fast, because modern JavaScript engines actually have some pretty clever optimization strategies. What they do is to create a very unoptimized version of machine code in the beginning, just so that it can start executing as fast as possible. Then, in the background, this code is being optimized and recompiled during the already running program execution. And this can be done multiple times, and after each optimization, the unoptimized code is simply swapped for the new, more optimized code without ever stopping execution, of course. And this process is what makes modern engines, such as V8, so fast. And all this parsing, compilation, and optimization happens in some special threads inside the engine that we cannot access from our code. So completely separate from the main thread that is basically running in the call stack, executing our own code. Now, different engines implement this in slightly different ways, but in a nutshell, this is what modern just-in-time compilation looks like for JavaScript. And the next time someone tells you JavaScript is an interpreted language, you just show them this slide so that they can learn how it really works. Alright, so we looked at the JavaScript engine and how it works behind the scenes in quite some detail. Now, to round off this lecture, let's also take a look at what a JavaScript runtime is, and in particular, the most common one, which is the browser. And by doing this, we can get the bigger picture of how all the pieces fit together when we use JavaScript. And so this is a really important slide. So, we can imagine a JavaScript runtime as a big box or a big container which includes all the things that we need in order to use JavaScript, in this case, in the browser. And the heart of any JavaScript runtime is always a JavaScript engine. So exactly the one we've been talking about. That's why it makes sense to talk about engines and runtimes together. Without an engine, there is no runtime, and there is no JavaScript at all. However, the engine alone is not enough. In order to work properly, we also need access to the web APIs. And we talked about web APIs before, remember? So that's everything related to the DOM, or timers, or even the console.log that we use all the time. So essentially, web APIs are functionalities provided to the engine, but which are actually not part of the JavaScript language itself. JavaScript simply gets access to these APIs through the global window object. But it still makes sense that the web APIs are also part of the runtime, because, again, a runtime is just like a box that contains all the JavaScript-related stuff that we need. Next, a typical JavaScript runtime also includes a so-called callback queue. This is a data structure that contains all the callback functions that are ready to be executed. For example, we attach event handler functions to DOM elements, like a button, to react to certain events, right? And these event handler functions are also called callback functions, okay? So as the event happens, for example a click, the callback function will be called. And here is how that actually works behind the scenes. So the first thing that actually happens after the event is that the callback function is put into the callback queue. Then, when the call stack is empty, the callback function is passed to the stack so that it can be executed. And this happens by something called the event loop. So basically, the event loop takes callback functions from the callback queue and puts them in the call stack so that they can be executed. And remember how I said in the last lecture that the event loop is how JavaScript's non-blocking concurrency model is implemented? Well, here is an overview of how that works. Now, we will go over why this makes JavaScript non-blocking in a special lecture about the event loop later in the course, because this is really a fundamental piece of JavaScript development that every developer needs to understand deeply. All right. So as I already said, the focus in this course is on JavaScript in the browser. And that's why we analyzed the browser JavaScript runtime. However, it's also important to remember that JavaScript can exist outside of browsers, for example in Node.js. And so here is what the Node.js JavaScript runtime looks like. It's pretty similar, but since we don't have a browser, of course we can't have the web APIs, because it's the browser who provides these. Instead, we have multiple C++ bindings and a so-called thread pool. Now, details don't matter here at all. I just want you to know that different JavaScript runtimes do exist. All right, cool. That's all I had to tell you about JavaScript engines and runtimes. In the next lecture, we will learn how JavaScript is executed in the call stack. In this lecture, let's answer the question, how is JavaScript code executed? We already know that it happens in a call stack in the engine, but let's dig a bit deeper now. And let's start by supposing that our code was just finished compiling, just in a way that we learned in the last lecture. So the code is now ready to be executed. What happens then is that a so-called global execution context is created for the top-level code. And top-level code is basically code that is not inside any function. So again, in the beginning, only the code that is outside of functions will be executed. And this makes sense, right? Functions should only be executed when they are called. And actually, we saw this happening already in our pick game project. So there we had an init function which initialized our entire project, but in order to actually initialize the game the first time that the page loaded, we needed to call that function immediately in our top level code. And so that's what I mean here. But anyway, we can also see what top level code is in this example here. So this name variable declaration is clearly top level code, right? And therefore, it will be executed in the global execution context. Next, we have two functions, one expression and one declaration. So these will also be declared so that they can be called later. But the code inside the functions will only be executed when the functions are called. Okay, so we know that a global execution context is created for top-level code. But now, what exactly is an execution context? Well, an execution context is an abstract concept, but I define it basically as an environment in which a piece of JavaScript is executed. It's like a box that stores all the necessary information for some code to be executed, such as local variables or arguments passed into a function. So JavaScript code always runs inside an execution context. And to make this a bit more intuitive, let's imagine you order a pizza at a takeaway. So usually that pizza comes in a box, right? And it might also come with some other stuff that is necessary for you to eat the pizza, such as cutlery or a receipt, so that you can actually pay for the pizza before eating it. So in this analogy, the pizza is the JavaScript code to be executed, and the box is of course the execution context for our pizza. And that's because eating the pizza happens inside the box, which is then the environment for eating pizza. The box also contains cutlery and the receipt, which are necessary to eat the pizza, or in other words, to execute the code. Okay? I hope that made sense and made the concept of execution context a little bit more clear. Now, in any JavaScript project, no matter how large it is, there is only ever one global execution context. It's always there as the default context, and it's where top-level code will execute. And speaking of execute, now that we have an environment where the top-level code can be executed, it finally is executed. And there is not a lot to say about the execution itself. It's just the computer's CPU processing the machine code that it received. Okay, and once this first code, so the top-level code, is finished, functions finally start to execute as well. And here is how that works. For each and every function call, a new execution context will be created containing all the information that is necessary to run exactly that function. And the same goes for methods, of course, because they're simply functions attached to objects, remember? Anyway, all these execution contexts together make up the call stack that I mentioned before, but more on that in a second. Now, when all functions are done executing, the engine will basically keep waiting for callback functions to arrive so that it can execute these. For example, a callback function associated with a click event. And remember that it's the event loop who provides these new callback functions, as we learned in the last lecture. Alright, so we know now what an execution context is, but don't really know what it's made of, so what's inside of it. And so let's find that out next. And the first thing that's inside any execution context is a so-called variable environment. In this environment, all our variables and function declarations are stored, and there is also a special arguments object. This object contains, as the name says, all the arguments that were passed into the function that the current execution context belongs to. Because remember, each function gets its own execution context as soon as the function is called. So basically, all the variables that are somehow declared inside a function will end up in its variable environment. However, a function can also access variables outside of the function, and we have already seen that in action throughout this course, especially in the projects of the previous section. And this works because of something called the scope chain. And we will learn all about scoping and the scope chain later in this section. But for now, what you need to know is that the scope chain basically consists of references to variables that are located outside of the current function. And to keep track of the scope chain, it is stored in each execution context. Finally, each context also gets a special variable called the this keyword. And once more, there is a special lecture just about the this keyword later in the section. Okay, now the content of the execution context, so variable environment, scope chain, and this keyword, is generated in the so-called creation phase, which happens right before execution. And now just one final but very important detail that we need to keep in mind is that execution contexts belonging to arrow functions do not get their own arguments keyword, nor do they get the this keyword. Okay? So basically, arrow functions don't have the arguments object and the this keyword. Instead, they can use the arguments object and the this keyword from their closest regular function parent. And this is an extremely important detail to remember about arrow functions, and we will come back to it later. So these are the things that are necessary to run each function, as well as the code in the top level. Now, behind the scenes, it's actually even more complex, but I think we're fine like this, aren't we? And now let's actually try to simulate the creation phase for this code example here. So, as you hopefully know by now, we will get one global execution context and one for each function. So one for the first function and one for the second function. In the global context, we have the name variable declaration, the first and second function declarations, as well as the x variable declaration. For the functions, the variable environment will literally contain all the code of a particular function. Now, the value of x is marked as unknown here because this value is the result of the first function that we didn't run yet. But we will simulate this in the next slide. Now, technically, none of these values actually become known during the creation phase, but only in the execution phase. So this is not 100% accurate here, but it's just to illustrate how these execution contexts work. Okay, so just keep that in mind. Anyway, now in the first function, we have the a variable set to 1 and the b variable, which once again requires a function call in order to become known. Finally, the variable environment of the second function contains the c variable set to 2, and since this is a regular function, so not an arrow function, it also has the arguments object. And this object is an array which contains all the arguments that were passed into the function when it was called. In this case, as you can see, that's 7 and 9. Quite simple, right? Well, it's simple because this is an extremely small amount of code. But now imagine there are hundreds of execution contexts for hundreds of functions. How will the engine keep track of the order in which functions were called? And how will it know where it currently is in the execution? Well, that's where the call stack finally comes in. And remember that the call stack, together with the memory heap, makes up the JavaScript engine itself. But what actually is the call stack? Well, it's basically a place where execution contexts get stacked on top of each other in order to keep track of where we are in the program's execution. So the execution context that is on top of the stack is the one that is currently running. And when it's finished running, it will be removed from the stack and execution will go back to the previous execution context. And using the analogy from before, it is as if you bought pizzas with some friends. Each friend has a pizza box, and then you put the boxes on top of each other, forming a stack, in order to keep track which pizza belongs to each friend. Now, all this sounds a bit abstract, doesn't it? And so to demonstrate how the call stack works, let's walk through this code example together so that I can show you exactly what happens. So, once the code is compiled, top-level code will start execution. And then, as we learned in the beginning of the lecture, a global execution context will be created for the top-level code, right? So this is where all the code outside of any function will be executed. And what happens with this execution context? That's right, it will be put in the call stack. And since this context is now at the top of the stack, it is the one where the code is currently being executed. So let's continue now with this execution. So here, there is a simple variable declaration, and then the first and the second functions are declared. So nothing fancy, but that's just how normal top-level code gets executed. But then, in the last line, is where things start to get interesting. Here we declare the x variable with the value that is going to be returned from calling the first function. And so, let's actually call that function. Now, what happens immediately when a function is called? Well, it gets its own execution context, so that it can run the code that's inside its body. Perfect. And what happens to the context? Well, again, it is put in the call stack on top of the current context, and so it's now the new current execution context. Great, so let's continue. So we have yet another simple variable declaration here, and this variable will of course be defined in the variable environment of the current execution context, and not in the global context, right? Then, right in the next line, we have another function call. So let's call that function and move there. And as you guessed, a new execution context was created right away for this second function. And once more, it is pushed onto the call stack and becomes the new active context. Now, what's important to note here is that the execution of the first function has now been paused, okay? So again, we are running the second function now, and in the meantime, no other function is being executed. The first function stopped at this point where the second function was called and will only continue as soon as this second function returns. And it has to work this way because, remember, JavaScript has only one thread of execution, and so it can only do one thing at a time. Okay? Never forget that. Now, moving to the next line, we have a return statement, meaning that the function will finish its execution. So, what does that mean for the call stack? Well, it basically means that the function's execution context will be popped off the stack and disappear from the computer's memory. At least that's what you need to know for now, because actually the popped off execution context might keep living in memory, but more about that later in the course. Anyway, what happens next is that the previous execution context will now be back to being the active execution context again. And so let's also go back to where we were before in the code. And I hope that by now you start to see how the call stack really keeps track of the order of execution here. Without the call stack, how would the engine know which function was being executed before? It wouldn't know where to go back to, right? And that's the beauty of the call stack. It makes this process almost effortless. So I like to use the analogy of the call stack being like a map for the JavaScript engine, because the call stack ensures that the order of execution never gets lost, just like a map does, at least if you use it correctly. Alright, so we returned from the second function, are back in the first function where we have this calculation, and then finally this first function also returns. And so here the same as before happens, so the current execution context gets popped off the stack, and the previous context is now the current context where code is executed. In this case, we're back to the global execution context and the line of code where the first function was first called. So here the returned value is finally assigned to x and the execution is finished. Now the program will now actually stay in this state forever until it is eventually really finished. And that only happens like when we close the browser tab or the browser window. Only when the program is really finished like this is when the global execution context is also popped off the stack. And this is, in a nutshell, how the call stack works. So hopefully it makes sense now that we say that JavaScript code runs inside the call stack. And actually, it is more accurate to say that code runs inside of execution contexts that are in the stack, But the general point is that code runs in the call stack, which is of course true. Great! Next up, we will learn some more about the variable environment and how variables are created. So stay tuned for the next video. Let's continue our journey of diving really deep into how JavaScript actually works behind the scenes. I really hope you have enjoyed it so far and are able to see the immense value that these lectures bring to the table. Now, after this lecture, there will finally be another coding lecture. So hang tight, we're almost there. But now let's get started with this lecture. So we learned in the last lecture that each execution context has a variable environment, a scope chain, and a this keyword. So in this lecture, let's learn what scope and the scope chain are, why they are so important, and how they work. And let's start by understanding what scoping actually means and learn about some related concepts as well. So scoping controls how our program's variables are organized and accessed by the JavaScript engine. So basically, scoping asks the question, where do variables live? Or where can we access a certain variable and where not? Now, in JavaScript, we have something called lexical scoping. And lexical scoping means that the way variables are organized and accessed is entirely controlled by the placement of functions and of blocks in the program's code. For example, a function that is written inside another function has access to the variables of the parent function. Okay? So again, variable scoping is influenced by where exactly we write our functions and code blocks. Okay, and now about scope itself. Scope is the space or environment in which a certain variable is declared. Simple as that. And in the case of functions, that's essentially the variable environment which is stored in the function's execution context. So if now you're asking yourself, what's the difference between scope and variable environment? Then the answer is that for the case of functions, it's basically the same. Now in JavaScript, we have the global scope, function scope, and block scope. And we will talk about these in a second. But first, let's also define what the scope of a variable is. So the scope of a variable is basically the entire region of our code where a certain variable can be accessed. Now, some people use the word scope for all of this, but I like to define all these concepts that we have here in a clear way because there are actually subtle differences. For example, if you take a close look at it, scope is not the same as scope of a variable, and so you should know about these subtle differences, right? And I know it might still sound all the same for now, but after looking at a couple of examples and writing some real code, you will understand everything I just showed you here. Anyway, let's now talk about the three different types of scope in JavaScript. So that's global scope, function scope, and block scope. And remember, scope is the place in our code where variables are declared. And when I say variables, the exact same thing is true for functions as well. Because in the end, functions are just values that are stored in variables. So first, the global scope is, once more, for top-level code. So this is for variables that are declared outside of any function or block. These variables will be accessible everywhere in our program, in all functions and all blocks. So really everywhere. Next, each and every function creates a scope, and the variables declared inside that function scope are only accessible inside that function. This is also called a local scope, opposed to the global scope. So local variables live in the function, so to say. And outside of the function, the variables are then not accessible at all. Again, this is technically the same as the function's variable environment, but we still need to give it the name of scope in this context, because blocks also create scopes. Anyway, in this example here, the now variable is 2037 inside the calc_h function, and therefore we can use it in the function to do calculations. But outside of the function, as we try to log it to the console, we get a reference error. So JavaScript is trying to find the now variable in this global scope, so outside of the function, but it cannot find it. And so there is going to be an error. And if you remember our pig game project from the previous section, that is also the reason why we had to declare a couple of variables outside of the init function. Remember that? So we had some variables declared in the init function, and then that gave us an error because other functions were trying to access these variables. But of course, they were in the function scope, and so they were locally scoped, and so we couldn't access them outside of that function where they were declared. And here it actually does not matter what kind of function we're using. So function declarations, function expressions, and arrow functions all create their own scope. Now, traditionally, only functions used to create scopes in JavaScript. But starting in ES6, blocks also create scopes now. And with blocks, we mean everything that is between curly braces, such as the block of an if statement or a for loop. So just like with functions, variables declared inside a block are only accessible inside that block and not outside of it. Now, the big difference is that block scopes only apply to variables declared with let or const. Okay? So, again, only let and const variables are restricted to the block in which they were created. That's why we say that let and const variables are block scoped. So if I declared a variable using var in this block, then that variable would actually still be accessible outside of the block and would be scoped to the current function or to the global scope. And so we say that var is function scoped. So in ES5 and before, we only had global scope and function scope. And that's why ES5 variables declared with var only care about functions, but not about blocks. They simply ignore them. Finally, also starting in ES6, all functions are now also block scoped, at least in strict mode, which you should always be using anyway. And just like with let and const variables, this means that functions declared inside a block are only accessible inside that block. Okay? And we will see examples of all that in the next video when we're gonna go back to coding. So, to recap, let and const variables, as well as functions, are block scoped. And if you already know other programming languages, block scoping is probably more in line with what you already know. Function scopes are weird for some beginners in the JavaScript world. And that's why block scopes were introduced in ES6. But now, to understand all this a little bit better, let's actually look at a more real and detailed example and also learn about the scope chain. And here we have some code with different functions and blocks, and we're going to take a look at the scopes that are in this code, as well as build the scope chain. And of course, we start with the global scope. As you can see, the myName variable is the only variable declaration that we have in the global scope. Now, technically, the first function also counts as a variable that is present in the global scope, but I want to keep it simple here, and so I will only consider variable declarations and no functions. All right? Just keep in mind that whatever I'm explaining here for variables also works the same for functions. Anyway, inside the global scope, we have a scope for the first function, because each function creates its own scope, remember? And what's in this scope? Well, it's the h variable that's declared right at the top of the function. Next, inside the first scope, let's now consider the second function, which will also create its own scope containing the job variable set to teacher. So as you see, we have a nested structure of scopes with one scope inside the other. But now comes the actually interesting part, because here in the second function, we have this line of code where we need the myName variable and the age variable, which were both not declared inside the current scope. But we really need these variables here, because otherwise we can't create this string here, right? So how can this be fixed? How will the JavaScript engine know the values of these variables? Well, the secret is that every scope always has access to all the variables from all its outer scopes. So from all its parent scopes. In our example, this means that the second scope can access the h variable from the scope of the first function. Of course, this also means that the first scope can access variables that are in the global scope, because that is the parent scope. As a consequence of this, the second scope will then also be able to access the myName variable from the global scope, because it has access to the variables from the first scope. And by the way, all this also applies to function arguments, but in this example, we just don't have any. And this is essentially how the scope chain works. In other words, if one scope needs to use a certain variable but cannot find it in the current scope, it will look up in the scope chain and see if it can find the variable in one of the parent scopes. If it can, it will then use that variable. And if it can't, then there will be an error. And this process is called variable lookup. Now, it's important to note that these variables are not copied from one scope to another, okay? Instead, scopes simply look up in the scope chain until they find the variable that they need, and then they use it. What's also extremely important to note is that this does not work the other way around. A certain scope will never ever have access to the variables of an inner scope. In this example, the first scope, for example, will never get access to the job variable that is stored in the second scope. Okay? So again, one scope can only look up in a scope chain, but it cannot look down, basically. So only parent scope can be used, but no child scopes. Anyway, with all this in place now, this line of code can be executed and print to the console, Jonas is a 30-year-old teacher, even though the myName and age variables were not defined in the current scope. All the engine did was to get them from the scope chain. And as you might be noticing, we have actually already done this before in our own code. We just didn't really understand what was going on and how it all worked. But now we do know how it works. Amazing, right? Anyway, we still have one more scope left here, and that's the one created by this block here. Remember that starting with ES6, not only functions create scopes, but also blocks. However, these scopes only work for the ES6 variable types, so for let and const variables. That's why the only variable that's in this scope is the decade variable. The millennial variable isn't declared with const or let, and therefore it is not scoped to just this block. Instead, the millennial variable is actually part of the first function scope. So again, for a variable declared with var, block scopes don't apply at all. They are function scoped, not block scoped. Let and const, on the other hand, are in fact block scoped. Okay? This is one of the fundamental things that you need to keep in mind about let, const, and var. and about scoping in general. So if you're taking notes, and I hope you are taking lots of notes, then this must definitely be in there. Now, about the scope chain, if the millennial variable is in the first function scope, then of course the second function scope also has access to it, even if it doesn't really need that variable. Also, the scope chain does of course apply to block scopes as well, and therefore, in or if block scope, we get access to all the variables from all its outer scopes. So from the first function scope, and of course from the global scope. That's why I said in the last slide that variables in a global scope are accessible from everywhere. They are because they are always at the top of the scope chain. In fact, we call variables in the global scope global variables. Very creative, right? But we actually use this term a lot in JavaScript. Now, it's important to understand that our purple block scope does not get access to any variables from the yellow second function scope, and the same the other way around. And why is that? Well, it's because of lexical scoping, as we learned in the last slide. So the way that we can access variables depends on where the scope is placed, so where it is written in the code. In this case, none of these two scopes is written inside of one another. They are both child scopes of the first function. We could even say that they are sibling scopes. And so by the rules of lexical scoping, they cannot have access to each other's variables, simply because one is not written inside the other one. We can also say that the scope chain only works upwards, not sideways. Okay, so this was a lot to take in, but I hope that everything still keeps making sense at this point. And if not, don't worry, we will see all this working in practice in the next video. But for now though, there is one more thing that we need to talk about, which is the difference between the scope chain and the call stack. I get a lot of questions about this all the time, and so I decided to talk about how the call stack, execution context, variable environments, and scope are all related to one another. So before we move on to the next video. And once more, let's look at some more code here. So we have three functions called first, second, and third in order to make this easier to understand. We start by calling the first function, which then calls the second function, which in turn calls the third function. So from what we learned before, the call stack for this example will look like this, right? One execution context for each function in the exact order in which they were called. I also included the variable environment of each execution context. For now, all this has nothing to do with scopes or the scope chain, all right? All I'm doing is creating one execution context for each function call and filling it with the variables of that function. And you can pause the video here for a moment to understand the content of each variable environment. Okay, and now that you did that, and we have all these variable environments in place, we can actually start building the scope chain. As always, we're going to start with the global scope. And the variables available in the global scope are exactly the ones stored in the variable environment of the global execution context. And given everything we've learned so far, that makes sense, right? And note that in this example, I am actually including functions in each scope, unlike we did in the previous slide. Now, in the global scope, we also call the first function, which is the reason why we have an execution context for it in the call stack. And this function, of course, also gets its own scope, which contains all the variables that are declared inside of the function. And once again, this is exactly the same as the variable environment of the function's execution context. However, that's not all, because now we already know about the scope chain. So the first scope also gets access to all the variables from its parent scope, thanks to the scope chain. Now, as we already know, the scope chain is all about the order in which functions are written in the code. But what's really important to note here is that the scope chain has nothing to do with the order in which functions were called. Or, in other words, the scope chain has nothing to do with the order of the execution contexts in the call stack. The scope chain does get the variable environments from the execution contexts, as shown by the red arrows here, but that's it. The order of function calls is not relevant to the scope chain at all. Alright? Really keep that in mind. Now, moving on to the second function now. Once again, its scope is equal to its variable environment. Also, it's lexically written within the first function, and so of course, it will have access to all its parent scopes as well. So we can say that the scope chain in a certain scope is equal to adding together all the variable environments of all the parent scopes. And so this is how scope and the scope chain are built in the JavaScript engine behind the scenes. Okay, now in the second function, we try to call the third function. But why does that work? Well, it works because the third function is in the scope chain of the second function scope, as we can see here in our scope chain diagram. It's a function in the global scope, or a global function, and therefore it's accessible everywhere. Of course, this will create a new scope along with the scope chain, as we already know. Great. So what happens in this third function? Well, we're trying to access variables b, c, d, and a here. D is no problem because it's right there in the third function's scope. So that one is easy. Then variable c is not in a local scope, and so JavaScript needs to do a variable lookup. So it looks up in the scope chain, looking for variable c, but it's not there. And of course it isn't, because c is defined in the second function, and there is just no way in which the third function can access variables defined in the second function. And that is true even though it was the second function who called the third. And so here is even more proof that the order in which functions are called does not affect the scope chain at all. And so here, as a result, we get the reference error because both C and B cannot be found in the third scope nor in the scope chain. Okay, and with this, I hope I made it crystal clear that execution contexts, variable environments, the call stack, scope, and the scope chain are all different, but still very related concepts. And if it's not yet crystal clear, then it's no problem to maybe rewatch this slide or maybe even this entire lecture a little bit later. And I know that this was quite a long lecture with a ton of stuff to take in, and so here is a handy summary with the main takeaways from this video. So to start, scoping asks the question, where do variables live? Or where can we access a certain variable and where not? That's what scoping is all about. Now, there are three types of scope in JavaScript: the global scope, scopes defined by functions, and scopes defined by blocks, starting in ES6. However, only let and const variables are block scoped. Variables declared with var automatically end up in the closest function scope. Next, in JavaScript, we have lexical scoping, which means that the rules of where we can access variables are based on where in the code functions and blocks are written. And now let the magic begin, because every scope always has access to all the variables from all its outer scopes. And this is what we call the scope chain. When a certain variable is not in the current scope, The engine looks up in the scope chain until it finds the variable that it's looking for. And this process is called variable lookup. It's important to note that the scope chain is a one-way street. So a scope will never ever have access to the variables of an inner scope, only of outer scopes. We can also think of the scope chain in a certain scope as being equal to adding together all the variable environments of all the parent scopes. And finally, we need to keep in mind that the scope chain has nothing to do with the order in which functions were called. So the order of function calls does not affect the scope chain at all. Okay, and now that's actually it. This is, in a nutshell, scoping in JavaScript. See you in the next video. Now it's time to see scoping in action in a semi-complex example to make sure that you really get this super important concept. And as always, let's start by opening up a new VS Code window with our starter files. So that's already here at my desktop. And again, I have the prettier configuration here. The index is not really important here. And so let's just start writing some JavaScript code here. And I'm going to start by writing a simple calc_h function. And this time, let's actually use a function declaration. Not that it matters, but just to have some diversity and not always create the same type of function. So calc_h, which is going to receive a birth year. And then all this function does is to calculate an age. And so this is nothing new at this point. So the current year minus the birth year. Then let's also return that age here. And so this calc_h function here is, as we learned in the last lecture, defined in a global scope. And that's because it is here in the top level code, right? Also, this function here creates its own scope, and that scope is going to be equivalent to the variable environment of its execution context. So that's all the stuff we learned over the past couple of lectures. And now let's create a global variable here. So I'm going to call that one first name. And now let's actually call the function. So calc_h with 1991. And then here inside of this calc_h function, I will log first name to the console. So first name. Now, as you see, this first name variable is not actually in this scope of the calc_h function. However, it is a global variable that we defined out here. And so therefore, through the scope chain, it's going to be made available also inside of this scope. So inside of this function, right? So let's just execute this code here just to see that it actually works. And then we're going to explain a little bit more. So live server. And so here we go. Let's open up the console. Let's reload to get rid of this error. And okay. So you see that indeed Jonas here was printed to the console, which is the first name variable. And so when this line of code here was executed, JavaScript did not find this variable in this scope. And so it did a variable lookup, where it looked up in the scope chain to see if it found the variable there. And indeed, the parent scope of the calc_h function is the global scope. And the first name variable is in there, and therefore JavaScript could then use that. Now here, if we tried, for example, just name, then JavaScript would also do a lookup, but it would not find this variable in the global scope. And therefore, we would get an error. Now with this variable, actually, we would get no error, as I explained to you in the beginning, this is kind of a special variable name that we should not use. So let's say I used last name. And so again, this variable is nowhere to be found. So even by doing a lookup into the parent scope, and so now when I save this, then I get this last name is not defined error. Okay. And so going back here to first name, then of course, everything works just the same. And that is true even though this variable here was actually defined after the calc_h function. But that's not a problem at all because remember that the code in the function is only executed once it's actually called. And so that happens after the declaration of the first name variable. So right here. And so at this point in the code, the first name variable is already in the global execution variable environment. So in the global scope, ready to be used. Okay, but let's actually get rid of this here. And let's create another function inside of this function. So function print_h, and this will print a nice string to the console. And as you also know already, it also creates a new scope. And let's create an output variable, which is going to be the string that we will build here. So output equals you are the age, and I forgot the curly braces, born in birth year. And then we simply log that message to the console. And now to actually see this result here, we need to, of course, call the function. So let's do that right here. So print_h. And now we get this string with all the data that we actually computed, and it works just fine. So we get the age that was calculated here, and also the birth year that was passed into this function. And so here again, we see the magic of the scope chain in action. So once again, the engine, as it is executing this print_h function, is trying to access or is trying to find the age variable in the current scope. However, it cannot find it there, and so therefore it goes to the parent scope where it will then find this age variable, of course, that we created here. And the same is true for the birth year variable, because for scoping, the parameter of a function works just like normal variables. And also remember that we say that the scope of a variable is the entire region of the code in which the variable is accessible. So for example, the scope of the age variable is all of this area here. So everywhere here, the age variable is accessible. So of course in the calc_h function where it was defined, and then also in all the child scopes, so all the inner scopes, okay? But of course, age is not accessible outside of the calc_h scope. So let me demonstrate that here. So here we will not be able to access the age variable. And that is because, as I mentioned, the scope chain is a one-way street. So only an inner scope can have access to the variables of its outer scope, but not the other way around. So now here we are in the outer scope, and we cannot have access to the variables of a child scope, which the scope of the calc_h function here surely is. Okay, and the same goes for functions again, and so we cannot call the print_h function out here for the same reason. So let's comment out this one. And so now we get print_h is not defined. Okay, so here in the global scope, we do not have access to any variables defined in any other scope. All right. And here let's actually take it to the next level and also include the name of the person. So let's say first name, and let's try this now. And indeed, it does have access to the first name variable. And so here the engine is doing an even bigger or longer variable lookup. So right now we are of course in the print_h scope here. And so then JavaScript cannot find the variable in the current scope. So it looks up in the scope chain, which is then the next step, the calc h function. However, it can also not find first name in this scope, and therefore it goes up even further into the global scope. And there it is. And so this is the value that is going to be used. Okay, so I hope all of this made sense until this point. Let's now go further and also create a block scope right here in this print h function. So let's do an if statement here. And we will check if the person based on the birth year is a millennial. And so that is if you were born between 1981 and 1996, then you're a millennial. And so let's check for that. So birth year needs to be at least 1981 and below 1996. And so here we are creating a block, and therefore this will be a new block scope. And so let's now define a variable here using const. And I'm going to call it string. And let's say, so first we get this string here to the console, and then we can also say, so if the person is a millennial, we will say, oh, and you're a millennial. And then again, the first name. And so now we are adding even one more step here to the scope chain, because now the lookup for first name is even longer. But it still will work. So let me log that to the console. And so in this case, I am clearly a millennial. Okay. And again, Jonas here is still found all the way here from the outer scope. But now, what do you think will happen as we try to log this variable outside of this block scope? So basically do the same, but outside of the block. So indeed, we get an error that str is not defined. And again, that's because const and let variables are block scoped. So they are valid. So they are available only inside the block in which they were created. But now watch as we create yet another variable, which I will call millennial. And let's set it to true. And so this is an old pre-ES6 variable. And so what do you think will happen as we log it also here outside of this block? So we need to comment out this one. So again, what do you think is going to happen now? And JavaScript can actually find it. And so that is because of the fact that var variables, so variables declared with the var keyword, are function scoped. So they simply ignore the block because they are not block scoped at all. They're just function scoped. And so here we are still in the same function. So here we are trying to access the variable that was defined in the same function, right? So right now, the scope of the millennial variable is this entire function, no matter if it was declared inside of a block or not. Because again, var variables do not care about blocks at all. And so therefore, we can then access the millennial variable inside of its scope. Okay? So keep that in mind as you use or as you see a variable declared with var, right? Because as I said, on your own, you should probably not use this variable yourself. Always just use const or let. But if you are reading other code bases or even working with older code, then keep in mind that this is how the var variable works. And so that's why it's very important to learn about this here as well. Okay, next up, let's prove that functions are also in fact block scoped starting in ES6. So let's just create a simple function here that will add two values. Return a plus b. And then let's attempt to call it here outside of the block. So add 2 and 3. And now we get add is not defined. And so, in fact, the scope of this add function here is only the block in which it was defined. So only here we can use the add function. And so that proves that functions are now in fact block scoped. But remember that that is only true for strict mode. And so that's the mode that we're actually currently in. But if I turn this off, you should see now actually add being called. So let's log the result of that to the console. And so we should now see 5. And indeed, now it works. All right, but we should always use strict mode. And so now we should get that error back. And so let's also comment this out. And so you can keep this here as a reference. Okay, and now to finish, let's do some experiments here. So what do you think is going to happen if we declare a variable in this scope here? So in this new block scope that already exists in a parent scope. So for example, let's say here, const first name equals Stephen. So what do you think this string here will look like now? So do you think that here it will say Jonas or Stephen? Well, let's try. And in fact, it now says Stephen. And that happens because, as always, JavaScript tries to look for the variable name in the current scope. And right now, it actually is in the current scope. So first name is indeed in this same block, so in this same scope. And so therefore, JavaScript will then use that variable and not perform any variable lookup in the scope chain. So the scope chain isn't necessary at all if the variable that we're looking for is already in the current scope. And so that's exactly the case right here. But of course, then outside of this block, the first name variable is still going to be the one coming from the scope chain. So that's why here you still see Jonas. So right here in the print h function, which is another scope, so it's the parent scope of this scope, right? And so here, first name is still Jonas, because it is not in the current scope of this function, and therefore JavaScript will make a variable lookup in the scope chain until it can find first name, which is still Jonas, coming from down here. So here we created a new variable with the same name of another variable that we had already created in a parent scope. So we have two first name variables right now, but that is not a problem at all, because in fact they are completely different variables. They simply happen to have the same name, but that's not a problem at all, because they are defined in different scopes. And so you can have repeated variable names. That's absolutely no problem. And that's also the reason why you can have different functions with the same parameter names. Because again, each parameter is only defined in that scope of that function. And therefore, it's not a problem at all to have many functions with the exact same parameter names, in the same way that it's not a problem to have functions with the same variable names inside of them. But now watch what happens when we redefine a variable from a parent scope inside of an inner scope. So not creating a new variable, but simply reassigning the value of a variable. So let's do that here. And let's now say output equals new output. And here we then have to change the output to a let. But let's just analyze what we did here. So we are in the print h scope. So that's all of this here. And in here we have the output variable. Then we have a inner scope, so like a child scope here, which then redefines this output variable from the outer scope. And so if we then try to access that output here again, what do you think is gonna happen? Well, we get new output here. And that is because we actually manipulated an existing variable here inside of a child scope, so inside of an inner scope, right? We did not create a new variable, we simply redefined a variable that we accessed here from the parent scope. So if we did create a new variable called output here, then we would have the same situation as before with first name. So this would then be a completely different variable and would not at all affect the output from the outer scope. And so now as we save this, then this new output should disappear and should be back to the original output as we defined it in the scope now. So indeed, now the new output is gone. And again, that's because it is now its own variable. So a brand new variable which just happens to have the same name as a variable from its parent scope. But to illustrate this here, let's actually leave it like this. And I will also comment it, creating new variable with same name as outer scopes variable. And let's put this together here. Reassigning outer scopes variable. So again, two completely different things, but I think this is a very nice example to once again illustrate how the scope chain works. And with this, I hope that you now completely understand how scoping works in JavaScript. Also, just keep in mind that real code should probably not be this confusing, but this was just to show you how scoping works. The next topic we need to talk about is a very misunderstood concept in JavaScript, and that is hoisting. So we learned that an execution context always contains three parts: a variable environment, the scope chain in the current context, and the this keyword. We already learned about the scope chain, and so now it's time to take a closer look at the variable environment, and in particular at how variables are actually created in JavaScript. So in JavaScript, we have a mechanism called hoisting. And hoisting basically makes some types of variables accessible, or let's say usable, in the code before they are actually declared in the code. Now, many people simply define hoisting by saying that variables are magically lifted or moved to the top of their scope. For example, to the top of a function. And that is actually what hoisting looks like on the surface. But behind the scenes, that's in fact not what happens. Instead, behind the scenes, the code is basically scanned for variable declarations before it is executed. So this happens during the so-called creation phase of the execution context that we talked about before. Then, for each variable that is found in the code, a new property is created in the variable environment object. And that's how hoisting really works. Now, hoisting does not work the same for all variable types. And so let's analyze the way hoisting works for function declarations, variables defined with var, variables defined with let or const, and function expressions, and also arrow functions. So function declarations are actually hoisted, and the initial value in the variable environment is set to the actual function. So in practice, what this means is that we can use function declarations before they are actually declared in the code. Again, because they are stored in the variable environment object even before the code starts executing. And I actually told you before that function declarations work this way, but now you understand why. It is because of hoisting. And just to make this table a bit more complete, so that it serves as a nice overview for you, I also show here that function declarations are block scoped, as we learned before. Just keep in mind that this is only true for strict mode. So if you're using sloppy mode, which you shouldn't, then functions are function scoped. Next, variables declared with var are also hoisted, but hoisting works in a different way here. So unlike functions, when we try to access a var variable before it's declared in the code, we don't get the declared value, but we get undefined. And this is a really weird behavior for beginners. You might expect that you simply get an error when using a variable before declaring it, or to get the actual value, but not to get undefined. Because getting undefined is just really weird. And it's not really useful either, right? And actually, this behavior is a common source of bugs in JavaScript. So this is one of the main reasons why in modern JavaScript we almost never use var. Now, on the other hand, let and const variables are not hoisted. I mean, technically they are actually hoisted, but their value is basically set to uninitialized. So there is no value to work with at all. And so in practice, it is as if hoisting was not happening at all. Instead, we say that these variables are placed in a so-called temporal dead zone, or TDZ, which makes it so that we can't access the variables between the beginning of the scope and the place where the variables are declared. So as a consequence, if we attempt to use a let or const variable before it's declared, we get an error. Also, keep in mind that let and const are block scoped, so they exist only in the block in which they were created. And all these factors together is basically the reason why let and const were first introduced into the language, and why we use them now instead of var in modern JavaScript. Okay, but now what about function expressions and arrow functions? How does hoisting work for these? Well, it depends if they were created using var or const or let. Because keep in mind that these functions are simply variables, and so they behave the exact same way as variables in regard to hoisting. This means that a function expression or arrow function created with var is hoisted to undefined, but if created with let or const, it's not usable before it's declared in the code, because of the temporal dead zone. So again, just like normal variables, right? And this is actually the reason why I told you earlier that we cannot use function expressions before we write them in the code, unlike function declarations. Okay, but now before finishing, let's take a more detailed look at this mysterious temporal dead zone. So in this example code, we're gonna look at the job variable. It is a const, so it's scoped only to this if block, and it's gonna be accessible starting from the line where it's defined. Why? Well, because there is this temporal dead zone for the job variable. It's basically the region of the scope in which the variable is defined, but can't be used in any way. So it is as if the variable didn't even exist. Now, if we still tried to access the variable while in the TDZ, like we actually do in the first line of this if block, then we get a reference error telling us that we can't access job before initialization. So exactly as we learned in the last slide, right? However, if we tried to access a variable that was actually never even created, like in the last line here where we want to log x, then we get a different error message saying that x is not defined at all. What this means is that job is, in fact, in the temporal dead zone where it is still initialized, but the engine knows that it will eventually be initialized because it already read the code before and set the job variable in the variable environment to uninitialized. Then, when the execution reaches the line where the variable is declared, it is removed from the temporal dead zone and it's then safe to use. So, to recap, basically each and every let and const variable get their own temporal dead zone that starts at the beginning of the scope until the line where it is defined. And the variable is only safe to use after the TDZ, so the temporal dead zone. Alright, now what is actually the need for JavaScript to have a temporal dead zone? Well, the main reason that the TDZ was introduced in ES6 is that the behavior I described before makes it way easier to avoid and catch errors. Because using a variable that is set to undefined before it's actually declared can cause serious bugs which might be hard to find. And I will show you a small example in the next lecture. So accessing variables before declaration is bad practice and should be avoided. And the best way to avoid it is by simply getting an error when we attempt to do so. And that's exactly what the temporal dead zone does. A second and smaller reason why the TDZ exists is to make const variables actually work the way they are supposed to. So as you know, we can't reassign const variables. So it would not be possible to set them to undefined first and then assign their real value later. Const should never be reassigned, and so it's only assigned when execution actually reaches the declaration. And that makes it impossible to use the variable before. Okay? Make sense? Now, if hoisting creates so many problems, why does it exist in the first place? I get this question all the time, and so let's quickly talk about that here. So, the creator of JavaScript basically implemented hoisting so that we can use function declarations before we use them, because this is essential for some programming techniques, such as mutual recursion. Some people also think that it makes code a lot more readable. Now, the fact that it also works for var declarations is because that was the only way hoisting could be implemented at the time. So the hoisting of var variables is basically just a byproduct of hoisting functions. And it probably seemed like a good idea to simply set variables to undefined, which in hindsight is not really that great. But we need to remember that JavaScript was never intended to become the huge programming language that it is today. Also, we can't remove this feature from the language now. And so we just use let and const to work around this. All right, great. And with all that being said, let's now work on some practical hoisting examples. Maybe it didn't seem like it, but hoisting is actually a fairly straightforward process. So let's just go through the different scenarios here, starting with variables. So let's just create 3 variables here using the 3 different ways of declaring them. So now a let for the job, teacher, and then const for the birth year. Let's just call it year 1991. And now let's try to use all of these 3 variables before declaring them just to see what happens. So, me, job, and year. So, from the rules that we learned in the previous lecture, what do you expect will happen now? Well, the first console.log results in undefined. And that's because variables declared with var are actually hoisted, but they are hoisted to the value of undefined. And so therefore, when we try to access them, undefined is exactly the result that we get. And so that's the reason why we see this here. Then on the contrary, we have this let variable. And so here we see that we cannot access job before initialization. And so that's exactly the kind of error that I showed you in the last slide. And the origin of this error is the fact that the job variable is still in the temporal dead zone here at this point, right? So remember that the temporal dead zone of a variable declared with let or const starts from the beginning of the current scope. And so that's basically here. So in this case, it's the global scope. So from the beginning of the scope until the point of the code where it is defined. And so here. And this means that at this point, of course, the job variable is still in the temporal dead zone. And the same is true for year. And so now we get the same error here for the year variable as well. All right. So let's comment out both of these. Let me just write here that this is hoisting with variables. And now let's try out functions. So let's create function declarations and function expressions here. So function, and again, I will use a simple add, and let me just call it add decl, which stands for declaration AB, and return A plus B. And now a function expression, so add expression and once more return A plus B. And now, since we're doing these two, let's also create an arrow. So add arrow AB and return A plus B implicitly. So I hope you remember that this is how the arrow function works. And now, once again, let's try to use these functions before they are defined. And so I will log them to the console, so the result of calling them, because they return something. And so we need to log the result to the console. So as you already know. So let's add 2 plus 3. And now what do you think will happen? Do you think that it will be undefined again, just like we have here with the var variable? Let's see. And no, we actually get the result of 5. And so indeed, we were able to call the function declaration before it was actually defined here in the code. All right. And now let's try the same for the other two. Expression and add arrow. But now I hope that you can already anticipate what is going to happen. And so indeed, we get an cannot access add expression before initialization. And so that's exactly the same error that we got before here with this let and const variables. And that's because this function here right now is simply a const variable too. And so it means that it's now also in the temporal dead zone, right? So again, we are simply assigning a function value to this variable. And since this variable was defined with const, it is now in the temporal dead zone, and therefore we get this exact same error message as before. And the same, of course, is going to happen with the arrow, right? But now let me show you what happens when we change these to var. So do you think that now it will work somehow? Okay, we still get an error, but it is another error message here. So right now, add expression is not a function. And once again, the same is going to be happening for the arrow. Okay, and now let's think about the reason for this different error message here. So as you already know, any variables declared with var will be hoisted and set to undefined. And now this add expression here is essentially that. It's a variable declared with var, and so right now it is undefined. And then here we are trying to call undefined, basically. So we are doing essentially this. So undefined, and then we are trying to call it. And so we should now get the exact same error. So you see, it's not a function. And in fact, let me show it to you here even better. So add arrow should now be undefined. And indeed, here it is. And once more, that is because we now declared these two here with var. Okay, so let's simply take both of these out. And for you to keep this as a reference, I will leave this one as a var and this as a const. But just know that both of them will not work. The only function that you can use before declaring it is the function declaration. Okay, so now we covered all the rules here and saw how hoisting works. But now let's show me a very cool example which can demonstrate a pitfall of hoisting. And so it's a mistake that we can easily make if we're not careful and at the same time use var to declare our variables. So let's just write example here. So to start, let's declare a fictional function here. So a function which is a function declaration, and that's important. So a fictional function that will delete the shopping cart. So let's say that we have like an e-commerce website or application. So let's simply log here all products deleted. And so this is a dangerous function, okay, that we should not be calling without care. Next, let's also declare a variable which contains the number of products. And so now I will use a var, and this will then show you once more why we should not use var. Products equals 10. And now here at the top of our code, we are going to write some logic which will delete the shopping cart whenever the number of products is 0. Now we already know that 0 is a falsy value, and so we can write this, right? So in this case, we want to call delete shopping cart. All right, so again, here we have var num products set to 10. But then here we have this logic in which we want to write that when there is no products, we want to delete the shopping cart. But now watch what actually happens. So we get all products deleted, even though num products is actually 10. So why did that happen? Well, it is because of hoisting. So at this point of the code here, the num products variable is in fact not 10. Instead, what is it? Well, it is undefined. And that's because of the way hoisting works with var variables. So we just show that to you very quickly. And so indeed, now here from line 71, which is this one, we get this undefined. And we know that undefined is also a falsy value. And so therefore, this code will then still execute even though we thought that num products is 10. But in fact, it's undefined. And so that will also trigger the execution of this if block here. Now, of course, this is just a fictional tiny example, but in a large code base with thousands of lines of code and without best practices, something like this can totally happen. And it's going to be a bug that will be hard to find. So what are these best practices? What is the conclusion of all this? Well, as a first step, as I told you many times, just don't use var to declare variables. Use const most of the time to declare variables, and let if you really need to change the variable later. Also, in order to write clean code, you should declare your variables at the top of each scope. That will just make your code at least look a little bit better. Finally, always declare all your functions first and use them only after the declaration. And this applies to all types of functions, even function declarations which are hoisted. So you could use function declarations before you declare them, but still, just don't do that. It's just not clean, okay? So what I just told you are the best practices, not the rules of how it works in JavaScript, all right? And now just to finish, since we're talking about the differences between let, const, and var here, let's just take 2 minutes to see yet another small difference between them. So let's again declare one variable for each. Let y equals 2. So the values don't matter at all here. And now let's just take a look at the window object in the console. Okay, x has been, of course, z here. And so let's now take a look here at the window object here in the console. And window is the global object of JavaScript in the browser. And you can see all kinds of stuff in here. For example, the alert window that we have used before, or also some other functions that we probably might have used already before. So I'm not going to go into that here. But what is important, so let's go all the way to the down here, and you can of course explore this by yourself in case you're interested in. But what matters here is that beside all these functions, we also get a property of x equals 1. And that's exactly the variable that we declared right here using the var keyword. However, we cannot find y or z here anywhere in this object. And that's because they were declared with let or const. And so variables declared that way do not create properties on the window object. So let me actually demonstrate this to you even better. So we can say, or we can test x equal window dot x. So here we are testing if x is actually a property of the window object. And so if it is, then of course x must be the same as window.x. And actually it is true. And now the same for y and z. And so in these cases, it is both false. So in conclusion, I just wanted to let you know that variables declared with var will create a property on the global window object. And that can have some implications in some cases. And again, you can take some time to explore the window object because it's quite interesting to see everything that is in there. All right, but with that being said, let's now finally move on to our next topic, which is going to be the this keyword. The this keyword is an extremely important concept to understand in JavaScript, and many beginners find it especially difficult. But don't worry, it's actually not that hard if you know exactly how the this keyword works. So the this keyword, or this variable, is basically a special variable that is created for every execution context, and therefore any function. In fact, we learned before that it's one of the 3 components of any execution context, along with the variable environment and scope chain that we already learned about before. Now, in general terms, the this keyword will always take the value of the owner of the function in which the this keyword is used. We also say that it points to the owner of that function. And that sounds very abstract, but we will see what that means in a second. For now, what's very important to understand is that the value of the this keyword is not static. So it's not always the same. It depends on how the function is actually called, and its value is only assigned when the function is actually called. So it's very different from a normal value in this regard. If we set, for example, x to 5, then x will always just be 5. But the this keyword, again, depends on the way in which a function is called. But what does that actually mean? Well, let's analyze 4 different ways in which functions can be called. And the first way to call a function is as a method, so as a function attached to an object. So when we call a method, the this keyword inside that method will simply point to the object on which the method is called. Or, in other words, it points to the object that is calling the method. Okay? And so let's illustrate this with a simple example. So the method here is the calcH method, again, because it's a function attached to the Jonas object. In the last line here, we then call the method, and as you see, inside the method, we use the this keyword. Now, according to what we just learned, what should be the value of the this keyword here? And that's right, it should be Jonas, because that is the object that is calling the method down there in the last line, isn't it? And so then, on Jonas, we can of course access all the properties that it has, and so this.year will become 1989, because that's Jonas.year as well. So in this case, writing Jonas.year would have the exact same effect as this.year. But doing it this way is a way better solution, for many reasons that we will get into throughout the course. And we will play around with this example a bit more in the next video. But anyway, another way we call functions is by simply calling them as normal functions, so not as a method, and so not attached to any object. In this case, the this keyword will simply be undefined. However, that is only valid for strict mode. So if you're not in strict mode, this will actually point to the global object, which in case of the browser is the window object. And that can be very problematic, and so this is yet another very good reason to always use strict mode. Next, we have arrow functions. And while arrow functions are not exactly a way of calling functions, it's an important kind of function that we need to consider. Because remember, arrow functions do not get their own this keyword. Instead, if you use the this variable in an arrow function, it will simply be the this keyword of the surrounding function, so of the parent function. And in technical terms, this is called the lexical this keyword, because it simply gets picked up from the outer lexical scope of the arrow function. So never ever forget this very important property of arrow functions. Believe me that actually I run into 1 or 2 bugs because of this behavior. Okay, so it's really important not to forget that arrow functions do not get their own this keyword. Okay, and finally, if a function is called as an event listener, then the this keyword will always point to the DOM element that the handler function is attached to. Very straightforward, right? Now, the this keyword is usually a big source of confusion for beginners. But if you know these rules, then it should become a lot simpler. And to make it even simpler, it's also important to know what the this keyword is not. So this will never point to the function in which we are using it. Also, the this keyword will never point to the variable environment of the function. And these are 2 pretty common misconceptions, and so that's why I'm addressing them here. Okay? So again, the rules that I showed you here is all that you need to know. Alright, and now just for the sake of completion, there are actually other ways in which we can call a function. For example, using the new keyword or the call, apply, and bind methods. But we don't know yet what any of these are, and so I will talk about how the this keyword works with them when the time comes. Anyway, that's it for this lecture, so let's now use this in practice to make it crystal clear. Let's now see the rules of how the this keyword is defined in action. And let's start by taking a look at the this keyword outside of any function whatsoever. So just outside here in the global scope. And so we get that the this keyword in the global scope is simply the window object. So that's the global object that we just saw before. Remember? And now let's do the same, but inside of just a regular function call. So we're going to use our old friend calc_h here. So let's log to the console just the usual result so that we're actually doing something here. But then what we're really interested in is taking a look at this keyword. So let's now call this function. And so let's see. And now the result of taking a look, so at logging the this keyword, is undefined. Okay. And so what that means is that inside this just regular function call here, the this keyword will be undefined. And that's because we are in strict mode. Remember that in sloppy mode, it would be also the global object. So in this case, the window object, but you already know that you always should use strict mode. And so then in a regular function call like this, the this keyword will simply point to undefined. And with a regular function call, I simply mean a call of this function without the function being attached to any object. So without having an owner, so to say. But now let's see what happens if this function here was an arrow function. So let's just copy this. So calc_h both here and here, arrow. And let's call this one with a different value. And now think about the rules that we learned in the last video. So what do you think the this keyword will be if this function is an arrow function? And actually we still need to do that. So birth year. And so now it is a legit arrow function. And so once more, what do you think the this keyword will now be? Think hard about it, and then let's check. And so it is window. So that's a little bit weird, maybe, right? So why is that? Why is the this keyword undefined in this function, but window in this function? Well, it is because the arrow function does not get its own this keyword. So instead, the arrow function simply uses the lexical this keyword, which means that it uses the this keyword of its parent function, or of its parent scope, so to say. And in this case, what is the lexical this keyword? So what is the this keyword in the parent scope of this function? Well, it is window, because window is the this keyword here in the global scope. So right here. Okay, that's why I started by showing you this one here. So in this case, this keyword here will simply point to the this keyword in the global scope. And so therefore, it will point to window. Unlike here in this normal function, which does actually get its own this keyword. It simply is undefined here, but it is its own this keyword. While this one here in the arrow function is actually not the this keyword of this function here. Okay, it is simply the this keyword of the parent scope. And that happens to be the window object in this case. In the next video, we will see some more real-world implications of the fact that the arrow function does not get its own this keyword. Now, next up, let's try to use the this keyword inside of a method. So let's quickly create a Jonas object here, just with a birth year, 1991, and then again our calc_h method. And so remember that this is basically now a function expression that we need to write here. And now let's log the this keyword here. And then let's call actually the calc_h function. For now, just to see what the this keyword will look like. And my hope is that you can guess already what it should look like. So let's save it to see the result. And indeed, it is the Jonas object. So exactly this object with calc_h and year. And so it means that's exactly this object. And that's exactly the rule that I told you in the previous lecture. So when we have a method call, the this keyword inside of the method will be the object that is calling the method. And in this case, that's the Jonas object. So Jonas here is basically the owner of the method. That's another way of saying it. And therefore, inside of calc_age, this is Jonas. And then we can use that to our advantage to calculate the age here based on the data that is already in this object. And so that's one of the big use cases for the this keyword. Right? Because then we don't have to pass in this data here again. So instead of having to do this again, we can simply use the birth year that is already in the object itself. And so we can use the this keyword to reference that object. And so this should now give us our usual value here of 46. Great. So that's pretty important stuff. And now let's move on just to one final example here in this lecture. So I keep saying that the this keyword will point to the object that is calling the method, right? And that means that the this keyword will not simply point at the object in which we wrote the method. So here we wrote the calc_age method inside of the Jonas object. And so we might think that that is the reason why the this keyword points to Jonas. But that is not true. The reason that the this keyword will point to Jonas in this case is because Jonas was the object calling that method. And that's a subtle but very important difference. And let me now show you why that is. So let's create a new object, which I'm going to call Matilda. And let's create a first name. Or actually, we don't need a name. Let's just say year 2017. And that's it. That's all we need in this object. Now, remember that a function is just a value, right? And therefore, we can do this. We can say Matilda.calc_age should be equal to Jonas.calc_age. So basically, here we simply copy the calc_age method from Jonas to Matilda. And so now when we take a look at Matilda here, then we see that the calc_age function is also in here. All right. And of course, it's still also in Jonas, but now we copied it from one object to the other. And this is called method borrowing. So we basically borrowed here the method from one object to the other, and so we don't have to write it in a duplicate way. So now let's say Matilda.calc_age. And what do you think the this keyword will look like now? And let's get rid of some of these before so that they don't clutter our output here. And you can then, of course, take them back if you want to see them in your own code. But now let me save this and see what the result of this calc_age will be. So the age of Matilda gave us the correct result of 20, which is exactly 37 minus 27. And so this means that in this method call here, the this keyword does now actually point to Matilda. And we can also see that here. So here, as we logged the this keyword, we see that it's actually the Matilda object because of this birth year. And so this proves exactly what I was just telling you before, which is the fact that the this keyword always points to the object that is calling the method. And so here we are calling the method on Matilda, right? And so therefore, the this keyword will point to Matilda, which was the object which called the method. So even though the method is written here inside of the Jonas object, the this keyword will still point to Matilda if it is Matilda who calls the method. Okay? And so that's really important to understand. And it's the reason why I said in the last video that the this keyword is really dynamic. It's not static, and it depends on how the function is called. And we can take this even further by basically completely taking the function out of the Jonas object. So let's create just a variable called f for function, and then say jonas.calc h, and not call it, of course. So we just want to copy now the function into a new variable. And so once more, that is possible because a function is just a value. So we take this value here and copy it here. And of course, without calling it, okay? Just like here, where we copied the method from one place to the other, but we did not call it. So here we can take a look at f in the console. And so you will see that it's actually this function. But now, what implications is this going to have for the this keyword? Well, let's just try to call the f function, which remember is the code of jonas.calch. And so now the this keyword should be undefined. And therefore we also get this error that it cannot read year of undefined. So that's coming from here because the this keyword is now undefined. And so undefined.year does of course not exist. So this happens because this f function here is now just a regular function call, right? It is not attached to any object. There is no owner of this f function anymore here at this point. And therefore, it is just a regular function call, just like here, for example. And so therefore, the this keyword is then also undefined, just like, again, here in this function, which was also a regular function call, just like our f function is now. All right, so again, that's a subtle difference in our code, but it makes all the difference in the result that we then get. And for sure, the this keyword is a subject that confuses many beginners in JavaScript. But hopefully this lecture and the previous one made it a little bit more clear. Now we didn't talk about the event handler functions here that I also showed you in the last video, so on the slide there, but I'm leaving that for the advanced DOM section where we will come back to this. But for now, in the next video, we need to take an even more closer look at regular function versus arrow functions. Let me now show you some pitfalls of the this keyword related to regular functions and arrow functions. This way, we can learn when we should use and avoid each of them. And to start, let's get back the Jonas object from before. And I will also add a first name property. All right. And now let's add a second method here, but this time using an arrow function. So we will do a very simple greet method. And so an arrow function here, which simply logs to the console, hey, and then the name. And so we're going to take this name from the object. So this dot first name, or at least that's what we think we're doing. So let me now show you what happens as I call jonas.greet. And maybe you can also anticipate it based on the knowledge that you already have of the this keyword when used in an arrow function. So let's see what the result is here. And we get hey undefined. So that's not hey Jonas as we might have expected. And the reason is exactly the one that I mentioned in the last lecture, which is the fact that an arrow function does not get its own this keyword. It will simply use the this keyword from its surroundings. So in other words, its parent's this keyword. And the parent scope of this greet method is the global scope. Okay, just note here that this is actually not a code block. So you might think that like this kind of block here also creates its own scope, but it doesn't. So this is not a code block, it is an object literal. So it's just a way that we literally define objects. Okay, So all of this here is in the global scope still. And so therefore that includes this greet method. It is in the global scope. And so therefore the arrow function here, which does not have its own this keyword, will use the this keyword from the global scope. And remember, that is the window object, right? And so this dot first name is also undefined. And I think that this is actually something that we haven't seen before. So when we try to access a property that doesn't exist on a certain object, we do not get an error, but simply undefined. And so that is what is happening here. That's why we get undefined, because this is the window object. So just as we saw before, and then on the window object, there is no first name, and so we get undefined. Okay? And actually, this behavior can become pretty dangerous in case we use var to declare variables. Because remember from a previous lecture that variables declared with var actually create properties on the global object. And so let's imagine we have this. So var first name equals Matilda. And so now, as we run the greet function, it will say, hey Matilda. Okay, so why is that? So again, it is because inside of this function here, the this keyword is window. And actually, let me print that here to the console as well, just so we can really see that here happening. Okay, so again, window is the this keyword inside of this arrow function, even though that arrow function was called by the Jonas object. But that rule does not apply here because, again, it's an arrow function. And so if we take a look at this window object now, and here close to F for first name, you see here that it does indeed have a property called first name with the value of Matilda. And again, that's because if we declare variables with var, that creates these kind of properties on the global object. And so therefore, this dot first name, which translates to window that first name, is then Matilda. And so that's why we then get hey Matilda here. So that's yet another reason not to use var. So you see there's a pretty long list against var. So from this example, the big takeaway is that as a best practice, you should never ever use an arrow function as a method. And in my opinion, that's even true if you're not even using the this keyword in a particular method. Because if you have this rule of never using an arrow function as a method, then you never have to think about which type of function you should use. You will always just use a normal function expression, and like this, you will then prevent this kind of mistakes from happen. So this mistake that we saw here with hey Matilda is easy to prevent by simply not using var. But even then, hey undefined is still a bug. It's still not correct. And so that would have easily been avoided by just using a regular function. Right? If we had this, then of course now this object Jonas, which is calling the function, would then be the this keyword. Right? So you see first name Jonas and then hey Jonas. Because now this method actually does get its own this keyword. But let's put it back. And okay. Great. And now one final example of a pitfall of the this keyword is when we have a function inside of a method. And that is a pretty common thing to happen. And so let's now take a look at an example of that. So let's create another Jonas object here. Or actually don't. Actually, let's just use this object here that we already have. And let's enhance this calc_h method. So what I want in here is a function that will basically return if the person is a millennial. So easy enough, let's create an is millennial function in here. And let's simply log to the console if this dot year is greater or equal 1981. And so that's the same rule that we used before, so that the birth year needs to stay between 1981 and 1996. So below 1996. And then let's also call that function right here. So is millennial will be called as we call the calc_h function. So let's also do that. So jonas.calc_h. So we're calling this method here, the calc_h method, which is a regular method, so not an arrow function. And so therefore, the this keyword right here should be the Jonas object. But then in here, we have a regular function, so this one, and here we are then calling it again. Now inside of this function, we are using the this keyword. And so let's now see what happens as we reload the page. And we get cannot read property year of undefined on line 138. So that's right here. So what this means is that the this keyword must be undefined. That's what it says here. So let's just log that as well. And here we can get rid of this one now. Okay, and indeed, the this keyword here is undefined. So why is that? Well, if we think about this, then this here is really just a regular function call, isn't it? It is a regular function call even though it happens inside of a method. And the rule says that inside a regular function call, which this clearly is, the this keyword must be undefined. And so therefore, it is undefined right here. So this is just as if this function was outside of this method. So if we copied this function out here, we would get the exact same result. Now, some people consider that this is a bug in JavaScript, but in my opinion, it's not really. It's just how the this keyword works. It's a clear rule that a regular function call has the this keyword set to undefined. And so that's just what is happening here. Now, there are two solutions to this problem. The first solution is to use an extra variable that we usually call self. So outside of the function, let's say self, and then we set that to this. Because here we are still outside of this is millennial function. And so here we still have access to the this keyword set to Jonas, right? And so then in here, we can use simply self. And let's do that just here. And here I will duplicate this line so that we can keep the original one. And so now let's use self here. And so then through the scope chain, this self will be equal to this. So self is referenced here, but it's not, of course, in the scope. And so JavaScript goes up the scope chain into the parent scope, which is calc_h. And so here is where self is defined, and it is defined as this. So as the this keyword. And so this is a way in which we can preserve the this keyword. This can also be called that, so that you might also see. And so as we reload now, this actually works. So now we get the value of true. So this was kind of the pre-ES6 solution, but you might still find this solution in some older code bases. However, now in ES6, we have a more modern and better solution. And that solution is to use an arrow function. All right. So let's actually copy all of this because I want to preserve both versions here. And now I will just comment out this first. Let's say solution 1. But now here we have solution 2, which does not need this extra variable. Okay, So let's get rid of this, bring this back, and here, this again. And now, again, the solution to the problem that we saw before is that we can now use an arrow function. And that is going to work because the arrow function does not have its own this keyword. Right? So let's remember again that when we just call this, we get that the this keyword is undefined. And that's because a regular function gets its own this keyword. But the arrow function will not. It will simply use the this keyword of its parent scope. And in this case, that will be the calc_h method. And in here, the this keyword is Jonas, so the Jonas object. And therefore, then, here in an arrow function, that would also be the this keyword. And then it is going to work as expected. And indeed, now it is true. And again, this worked because this arrow function uses the this keyword from its parent scope. And in this case, in the parent scope, the this keyword is Jonas. So basically, an arrow function inherits the this keyword from the parent scope. And that is exactly what we need here. All right. And so here you see that it's pretty important to know exactly how each of the different type of functions work in regard to the this keyword, because then you can really use them according to your specific needs. Great. So I hope that especially this solution here made sense to you, and that when you need it at some point in your journey or in your job, you can remember that this is a very useful use case of the arrow function. Now, just to finish this lecture, I also want to quickly touch on the arguments keyword. Maybe you remember me talking about that also in a previous lecture. So in the video about execution contexts and the call stack, we learned that functions also get access to an arguments keyword. So not just the this keyword, but also an arguments keyword. Now, just like the this keyword, the arguments keyword is only available in regular functions. So let's create another function here. So first an expression. So again, basically that's our functions for adding. And actually, let me just grab them from here. I think I defined them somewhere up here. Yes. So there's no need to rewrite the same code over and over again. You just add a comment here, arguments, key, word. And then let me also print to the console that keyword. So let me quickly call this function here now. So 2 and 5. So just so we see the arguments keyword. And so down here it is. And you see that we get basically an array with 2 and 5. And so that's exactly the two parameters that we passed in. And this can be useful when we need a function to accept more parameters than we actually specified. So this is something that we never did before. So up until this point, we have only ever specified exactly the arguments that we have here in the list of parameters. So we have 2 parameters and so 2 arguments. But it is completely legal to add more arguments. They will not have a name, so we didn't name them, but they exist. And we can see them here in the arguments array. All right? So they do appear here, and we can use them, therefore, in the functions. For example, we could use a loop and then loop over this array and add all the numbers together. But now my point here is that the arrow function does not get this keyword. So let's also log it to the console here. So let's put this here in curly braces. Then remember, when we have more than one line of code, we need to explicitly return. And so let's try to take a look at the arguments keyword here as well. So add arrow 2, 5, 8, let's say. But then we get an error. So arguments is not defined. All right. So this was simply just to show you that the arguments keyword exists, but that it only exists in regular functions. So in function expressions like this, but also in function declarations, but not in an arrow function. But anyway, the arguments keyword is not that important in modern JavaScript anymore, because now we have a more modern way of dealing with multiple parameters. But still, it's important that you are aware that this arguments keyword exists. All right. And now with all these lectures on regular functions and arrow functions, you should know all the differences between them and, even more importantly, when to use each of them. As we move towards the end of this section, we need to learn about the big difference between the way primitive types and objects are stored in memory. And this is actually a very practical aspect, and one that causes a lot of confusion in beginners. So let's actually start by writing some code this time to understand what the confusion actually is, so that I can then show you how it all works behind the scenes. So right now, I'm not gonna explain how the code we will write now works, but I will just show you what the source of confusion is. But for now, let's start with a simple example with primitives. And so remember, primitives are like numbers, strings, booleans, etc. So simply setting the age to 30. And then I'm creating a old age variable. And this one I will set to the age, because now it is my birthday basically. And so my age changes to 31. But I still wanted to preserve my old age here in this variable. Okay, so let's log the results to the console now. And they should be pretty much what we expect at this point. So you see that my current age is 31 because, well, I changed the original one from 30 to 31. But the old age is still 30 here. And that's because I set it here at this point of the code to age, which was still 30 at this point. And so then changing the age here from 30 to 31 did of course not affect the old age variable. Again, because at this point here, age was still 30. All right. So here, hopefully there is not much confusion. Everything works just as expected. But now let's create another scenario which has an object. So I'm simply going to create an object for me with the name of Jonas and age 30. And now let's copy this object, because let's say that I have a friend who's also called Jonas. And so instead of creating a brand new object from scratch, I will just copy the me object. So const friend equals me. Okay? And so now both the name and the age are the same, but let's say that we have different ages. And so let's change the age of my friend. And that's pretty straightforward, right? So let's say that he is 27 years old. But of course, we did not change me.age, right? So let's now take a look at both of them in the console. So first my friend. So that's the friend object. And then also me. Or we could say Jonas, it doesn't really matter. But what matters is that we will see the me object. And what do we think will happen now? So let me show it to you. And now we get that both me and my friend have the age of 27. And that looks a little bit strange, because all we did was to change the age of the friend, right? Nowhere here I have me.age equals 27. But still, for myself, so here at the me object, the age is also 27. And so that is what I mean by source of confusion. And so in this video, let's now find out why it works this way. Now, before we can understand the code that we just wrote, we need to review some basics here. First, we need to remember about JavaScript's primitive data types, which are number, string, boolean, undefined, null, symbol, and big int. Then everything else are basically objects. So objects created with the object literal, arrays, and even functions are all objects. Now, when we're talking about memory and memory management, it's usual to call primitives primitive types and objects reference types because of the different way in which they are stored in memory. Next, we need to remember about the JavaScript engine. So the engine has two components, the call stack where functions are executed and the heap where objects are stored in memory. And that's right, all our objects, or in other words, reference types, will get stored right in the memory heap. And I mentioned that when we first talked about the engine, but now you will finally learn how that actually works. On the other hand, primitives, or primitive types, are stored in the call stack. And with that, I mean that primitive types are stored in the execution contexts in which they are declared. But for the sake of simplicity, let's ignore that detail now and simply say that primitive types are stored in the call stack, because that's where execution contexts run. Alright, but now how does all that actually work? And why did our code example earlier behave in that weird way? Well, let's find out. So here we have the two code examples from earlier, as well as the engine with call stack and heap. And let's start by looking at the primitive values example. So when we declare a variable like age equals 30, what actually happens inside the JavaScript engine and the computer's memory? Well, first, JavaScript will create a so-called unique identifier with the variable name. Then a piece of memory will be allocated with a certain address, so 0001 in this example, and finally the value will be stored in memory at the specified address. So in this case, the value 30 will be specified at memory address 0001. And remember, this all happens in the call stack where primitive values are stored. Now, what's extremely important to understand here is that the identifier actually points to the address and not to the value itself. So we would say that the age variable is equal to 30, but in fact, age is equal to the memory address 0001, which holds the value of 30. All right? And this subtle distinction is very important to keep in mind. Now, in the next line, we declare old age to be equal to age. So, knowing that a variable actually holds a memory address, what should old age look like? Well, it will simply point to the same memory address as the age variable. And so, it will look like old age is simply 30 as well. Great, but now in the next line, we set age to 31. So what will happen then? The value at address 0001 will certainly not become 31, because that would change old age as well, since they both point to the same address. So that would make no sense at all. Also, the value at a certain memory address is immutable, or in other words, it cannot be changed. So instead, what's going to happen here is that a new piece of memory is allocated, so is created, and the age identifier now simply points to the new address, which is holding the new value of 31. All right, and that's why when we lock both our variables to the console in the end, they both return exactly the values that we expect. Now with reference values, things work a bit differently, which is the reason why this example gave us that unexpected weird behavior earlier in practice. So what's the origin of this weird unexpected result? Well, when a new object is created, such as this me object, it is stored in the heap. And such as before, there is a memory address and then the value itself. Now, in the case of reference values like this me object, the me identifier does actually not point directly to this newly created memory address in the heap. So in this example, D30F. Instead, it will point to a new piece of memory that's created in the stack. And this new piece of memory will then point to the object that's in the heap by using the memory address as its value. In other words, the piece of memory in the call stack has a reference to the piece of memory in the heap which holds our me object. Okay? And that's the reason why we call objects reference types in this context. So again, when we declare a variable as an object, an identifier is created, which points to a piece of memory in the stack, which in turn points to a piece of memory in the heap. And that is where the object is actually stored. And it works this way because objects might be too large to be stored in the stack. Instead, they are stored in the heap, which is like an almost unlimited memory pool. And the stack just keeps a reference to where the object is actually stored in the heap so that it can find it whenever necessary. Now, moving on in the code, we create a new variable called friend that we set equal to the me object. So, what will happen here? Well, just like with primitive values, the friend identifier will point to the exact same memory address as the me identifier. And again, that address contains the reference, which then points to the object itself. And like this, the friend object is now essentially the exact same as the me object. Do you see that here in the diagram? So here comes the interesting part, because now we're actually going to change a property in the friend object by setting friend.age to 27. So what happens then is that the object is found in the heap and the 30 is changed to 27. Great. And by the way, even though we defined the friend variable as a constant, we can actually still manipulate the object without problems. And when we think about that, it makes sense, because we're actually not changing the value in memory for the friend identifier. It is still D305, so the reference to the object. All we did was to change the value in the heap, and that's not a problem. So it's a misconception that all variables declared with const are immutable. In fact, that is only true for primitive values, but not for reference values. So keep that in mind whenever you're working with const. Anyway, as we log the friend variable to the console, we get the age of 27, just as we said it before. But then, when we log the me object, we get that weird behavior that we could previously not explain and not understand. But with everything that we learned in this lecture, it actually now makes sense that in the me object, age is now also 27, even though we never changed me.age directly. And the reason for this, as we can see in this slide, is the fact that me and friend actually point to the exact same object in the memory heap. So whenever we change something in this object, it will always be reflected in friend and in me. So in both these objects. So these are basically just two different identifiers pointing to the exact same value. And once again, that value is the memory address D305, which points to the reference in the memory heap. And one important implication of this is that whenever you think that you're copying an object, you're really just creating a new variable that points to the exact same object. And this has huge implications for the way JavaScript works in practice, and we will see that in the next video and throughout the course. Now, there are actually ways around this, as we will also learn later, But in general, this is how reference values work in JavaScript. So make sure to really understand this, as well as the implications that this behavior has, even if that means that you have to rewatch this lecture, or at least the explanation of this slide. All right? Then, once you really understand what happened here in this example, let's understand primitive values and reference values even better in practice in the next lecture. But before we do that, let me just quickly take a second and mention 3 more really big topics about how JavaScript works behind the scenes that will not be in this section, but closer to where we actually need to learn about them. For example, one fundamental concept of JavaScript is prototypal inheritance, but we will only talk about that in the object-oriented programming section of this course, because it doesn't make sense to learn about this now, only to then forget it all until we finally reach that section. The same is true for a detailed lecture on the event loop. So I already introduced the event loop in this section, but in the section about asynchronous JavaScript, we will dive really deep into how exactly the event loop works and why it's such a fundamental piece of the JavaScript engine. Finally, we will have lectures on how the DOM actually works behind the scenes too. And that's going to be in the advanced DOM and events section, so that you can then apply what you learned there right away. Okay? And with that being said, let's now move on. Let's now create a similar example to what we had in the last video, just so that we can actually see this happening in practice. And just like in the last video, let's start by mutating a primitive value. So let's now use the last name, and I'm going to set it here to Williams. And so that's the initial value of this last name. Then let's also copy it. And so that's because, let's say that this person gets married and decides to change their last name. However, we still want to remember the old name, and so we say old last name is equal to the current last name at this position of the code. But then we mutate actually the last name to Davis. So basically when this person gets married, they then change their last name to Davis. And of course, if we now check out both of them, so first the last name and then the old last name, then we see that they are in fact different. So Davis is the new last name, so the one that we mutated here, and Williams is this old last name that was copied right here in this first line of code, or actually the second line of code. So here everything works as we would expect in an intuitive way. Now remember that it works this way because each primitive value will simply be saved into its own piece of memory in the stack. Okay? But now let's do the same thing with an object, which, as we already know, is a reference value, because it is going to be stored in the heap, and the stack then just keeps a reference to the memory position at which the object is stored in the heap. So let's create an object called Jessica. And so here we will have a first name of Jessica and a last name of Williams. Let's also give her an age of 27, just to make it more complete. And now let's again say that Jessica will get married and will therefore change her last name. And so this time, let's create a new object for the married Jessica. So married Jessica, and it should be equal to Jessica. So we're copying the entire object here. At least that's what it looks like. But behind the scenes, we are actually just copying the reference, which will then point to the same object. Remember that? And so now as we change the last name on married Jessica, so last name, let's change that to Davis. But as we already know, this will not give us the result that we expect. So before marriage, let's log this original Jessica object, so to say. And then after marriage, and then here the married Jessica object. Giving it a save. And now as we see, we get before the marriage and after the marriage, both the last name of Davis. All right. So the last name Davis is now also in the original Jessica object and not just in the one that we copied. And now at this point, we already know why this happened. So just to remember that, it happened because when we attempted to copy the original Jessica object, it did in fact not create a new object in the heap. So this one, again, is not a new object in the heap. It's simply just another variable in the stack which holds the reference to the original object. So both of these two variables simply point to exactly the same memory address in the heap. And that's because in the stack, they both hold the same memory address reference. And so of course, it makes sense that if we change a property on married Jessica, it will also change on Jessica itself. So again, because they are essentially just two different names for the same thing. Now, this is also the reason why we can change properties in the married Jessica object, which was declared using a const here. And const is supposed to be for constants, so for things that we cannot change. However, what actually needs to be constant is the value in the stack. And in the stack, the value only holds the reference, which we are not actually changing. The only thing that we are changing is the underlying object that is stored in the heap. And that is okay to change. That has nothing to do with const or let. All right? That's only about the value in the stack. But if we change something in the heap, that has nothing to do with const or let. Now what we can't do is to assign a completely different object now to married Jessica. So for example, we could not say married Jessica is equal to this new empty object. So that will not work, because this new object will be stored at a different position in memory, and therefore the reference to that position in memory will have to change here in this variable. And therefore that does not work, because that is in the stack, and so since it is a constant, we cannot change that value in the stack. So we cannot change the value to a new memory address, and therefore this does not work. If it was a let here, then we could do this, what we have here. But since it's a constant, again, it is not allowed. So as a conclusion, completely changing the object, so assigning a new object to it, is completely different than simply changing a property as we did here. Okay? So it's a fundamental difference. So please make sure to really understand this. Anyway, what if we actually really wanted to copy the object so that we could then change one of them without changing the other? So let me show you a way in which we can do that. Let's first add some comments here once more. So primitive types, reference types, and then let's now say copying objects. All right. And actually, let's create a new Jessica object. Let me, in fact, copy it from here. So let's say Jessica 2. And so now, if we really wanted to copy this object, we could use a function called object.assign. And what this function does is to essentially merge two objects and then return a new one. So we could do this, object.assign, and then again we can use this function to merge two objects. And so what we can do is to simply merge an empty new object with Jessica2. And this will then create a completely new object where all the properties are really copied. All right, so the result of calling this function here with these arguments will be a new object. And so let's store that in Jessica copy. And now let's say that Jessica copy gets married. So the same situation as before, changing her last name to Davis. And now let's log both to the console just like here. So Jessica2, and then here it's Jessica copy. So let's see what happens now. And so it's these last two here from line 222 and 223, right? And so now indeed we can preserve the original last name Williams after we change the last name on this other object here. So this Jessica copy. And what this means is that this object now is indeed a real copy of the original. So all the properties were essentially copied from one object to the other. And so behind the scenes, what that means is that a new object was in fact created in the heap, and Jessica copy is now pointing to that object. So it has a reference to that new object. However, there is still a problem, because using this technique of object.assign only works on the first level. Or in other words, if we have an object inside the object, then this inner object will actually still be the same. So it will still point to the same place in memory. And that's why we say that this object.assign only creates a shallow copy and not a deep clone, which is what we would like to have. So again, a shallow copy will only copy the properties in the first level, while a deep clone would copy everything. And to illustrate this, let me actually show you what I mean. And so let's add an array here in this original object. So an array of family. And this is going to work as an example because an array is really just an object behind the scenes. So here I can prove my point to you with this. So we have now an array called family, okay? And so you see that now this array here is indeed in both objects. So, okay, so far so good. But now let's actually change that array in Jessica copy. So in this one, because as Jessica married, she also increased her family. And so let's now add some more family members there. So Jessica copy dot family, and then let's use the push method to add a new element to the end of the array. And let's add Mary, and let's also add another one. So family dot push, and let's add John. So remember, here we are manipulating the copied object, which is actually a copy, but now here we are manipulating an object that's within the object. So that's this object. And so now as we save this, it still looks the same, but that's because we need to log, of course, after this operation happens. And so now we see that both the objects now have a family with 4 members. Let's open this a little bit, give it some more space. And so indeed, now before the marriage and after the marriage, the family has all these 4 members. All right. So the last name was, of course, as we already saw, preserved. So the name before the marriage is Williams, and that was preserved because that's in the first level, and object.assign here took care of copying that property. And so that was not changed as we changed the last name in the copy. However, the family object is a deeply nested object. And so therefore, object.assign did not really, behind the scenes, copy it to the new object. All right. So in essence, both the objects Jessica2 and Jessica copy have a property called family, which points at the same object in the memory heap. And that object is, of course, this array. And so when we change the array in one of them, it's also going to be changed in the other one. Now, a deep clone is what we would need here, but it is not easy to achieve. And it would actually be beyond the scope of this video to learn how to create a deep clone. Usually we do something like this, which is like really complex, using an external library, for example, like Lodash. And this library has a ton of helpful tools, and one of them is for deep cloning. And actually we will do that in a later section, just so you see how we can include an external library to do this kind of stuff. All right, and with this, we actually finish this section about how JavaScript works behind the scenes. And it was a long one with so many things and so many new concepts to learn. And many of them were hard and probably confusing, but that's not a problem. So it's always a part of learning. And even if you did not understand 100% of everything, you're still good to move on in the course to the next section now. But just reaching the end of this section already gave you a big advantage over many other developers which have no idea about many of the things that I showed you here in this section. So congratulations for sticking with it to the end and for learning all of this valuable knowledge. And now I see you in the next section.